Okay, so as we just discussed, we can compare the electrical field around a point charge and the electrical field between two plates. So just like we had, okay, so say if this point charge is positive, we have the electrical field is radiating out from it, but say if we look at point here, okay, this will be a weak electrical field, and here it will be strong. Okay, so just like in our example there. And we use this formula. Use E is equal to KQ over R squared. Because the electrical field strength depends on distance. Okay? Because our E depends on distance. So the closer the balloons got, the more electrical field strength there was, the farther away the less. So then you guys came up with this idea of parallel plates. So say these are our boys, they were positives, and then we had our girls were the negatives. All of the boys pointed toward the girls, okay? Oh, thanks. Okay, so now what actually happens to make these plates is that we put a battery, okay, to give it the charge, is how we make it, okay? Now, when you draw a battery, okay, on a diagram, the long end represents the positive end, okay, so this long is positive, and this short one is the negative, okay? This represents, this whole thing, this is a battery, okay? You can have multiple, like, layers of these, but that's the simplest one to show you. Yeah. Now, when we do this, this is called a uniform electric field. Uniform meaning that it's the same everywhere. Okay, uniform electrical field between parallel plates. Therefore, if you have a parallel plate question, you never use E is equal to KQ over R squared, because the electrical field strength doesn't depend on the distance between parallel plates, okay? So, parallel plates, we must need to use different formulas because the strength of the electrical field will depend on different things, okay? There is a factor of distance, okay? But what can I change for distance, do you think, to make the electrical field strengths different? Like, I can make the plates closer together. Would make the field strength bigger. Or if I brought them really far apart, the electrical field strength just wouldn't be as much. Okay. So there was one other word, and I'll show you more about that. There was one other thing that I talked about that said it was the electrical potential difference between the plates. What was that called? Starts with a V, and then we think about it with electric voltage. Yeah. So like the more voltage that it has, that the battery would give, okay, would increase the electrical field strength as well. So it's a whole different way of looking at our electrical fields, like completely different. We can't really apply very much from the other stuff to this, except for like the directions, you know? Okay, so let's get into, I'll explain a little bit. And you guys actually started doing this. This is great. You guys are so smart. So, parallel plates are an example of where the electrical field strength is uniform. Okay, very, very key word there. We need a different equation to deal with this uniform electric field strength because we can't use this one. So, when we think about it, you guys started to say this. Electrical potential energy is similar to our gravitational. A charged object inside a uniform field can have high electrical potential energy and low electrical potential energy. The law of conservation of energy applies, and electrical potential energy can be converted into kinetic, just as you guys said, right? Because the balloon would be moving and its kinetic energy would be increasing. Velocity change, acceleration. Okay, so say we have our parallel plates. Let's just put our negatives up here for fun. 8. And we have our positives down here. 8. Okay. So, and let's put our battery in. Negative, positive. So, just like our example we did, let's say I have in my negative balloon and I started at this end, just like we did with our example. Which way does it accelerate? Toward the positive plate. So it's moving this way. Okay? At this point where it was at the negative bar, you guys told me it has high what? What type of energy? Yellow question. Potential, yeah? And low EK, or basically EK could be 0. If it's not moving, you're just holding it there. And then at the very bottom, we have low EP and high EK. So we're seeing a lot of similarities with our electrical forces and our gravitational forces and the way we think about them. Okay, yeah, so you guys, man, aren't you glad that I made you think? Because now you know so much of this. Therefore, uniform electric fields and parallel plates are a method to accelerate or decelerate the charged particles, right? Because velocity was changing. Now, I'm going to tell you about an application of this. Remember back in Bio 30, we were doing DNA stuff, and we talked about gel electrophoresis? Okay, very old, I guess. This is what gel electrophoresis uses. DNA is naturally negatively charged. So what they would do is that they would make these parallel plates, put the DNA into the gel, and then turn on the battery. And the DNA would go toward the positive end, right? Depending on how large the DNA is, it would go a certain distance. Okay? And so then they could kind of make like almost like a fingerprint of your DNA, like your DNA would look a really specific way, like it would have these certain bands. Okay? So I'll just show you a picture. But it's like, you know, physics doesn't have to be all by itself. There's applications. So here, so say they set up these parallel plates and put a battery in. They put the DNA, okay, in the gels, and then they'll flow toward the positive end. And then you end up with something that looks like this. these are bands of DNA, and they would have like very specific lines. So this would be like the DNA from hair on a dog, and then this would be the DNA from hair on a cat. This would be like the DNA from the hair on a person. And you could take, like, say, hair from, you know, like a crime scene or something, and say, okay, who did it, you know? Well, it wouldn't be cats and dogs, but. So, that's an application of this. Yeah, kind of cool, hey? I know. Just calm down.